So we're gonna be moving on. We're gonna talk. I'm gonna review a little bit with capacitor and capacitance. You have your capacitor lab that you're gonna be working on this week. That you have. Make sure you're working through that. Today's lesson will help kind of carry you the rest of the way through and give you the rest of the information you're gonna need for that lab. Um, this is also going to make that transition between that. We started talking about charge flowing and creating this light. Now we're going to start talking about that a little more and comparing things called voltage, current, resistance. We're going to get into what I like to call the quintessential equation for electronics. If you think of Newtonian, you usually think of like F equals ma. That's our base equation. That's the most common equation when you think about that type of our branch of physics. With electricity, Ohm's law that we're going to talk about today is that equation for electricity. So just like before, I'd like you to answer this question. So go ahead and take a look at it. How does a capacitor discharge and why? So thinking back to the previous lesson of looking at how we charged a capacitor and then got that light bulb. Why do those charges move and get off those plates and start flowing once they're connected to a light bulb? So go ahead and pause the video and take a minute to go ahead and answer that question. All right, so hopefully, as you think about this, you remember the idea that charges, when you separate them, don't want to be separated. Opposites attract. So if you start separating these positives and negatives charges, they want to try to find a way to get back to each other. They don't like that. And so when you create a path for them, connect the wires through that light bulb, you give that opportunity for those charges to start moving and equalize out, and opposites attract. And so you end up with no net field. Charges don't like to have that field there. They're going to move if they can. With a charged capacitor, they can't move unless they're given a path, and that's where the wires and what we're going to talk about with the circuit and the light bulb comes into play. So again, that's where we're starting with this question of how does a capacitor discharge and why is it discharging? And so we'll talk about that, how much charge is flowing, what's going to affect the amount of charge flowing, and what that flow of charge can actually do. So our learning targets here this for this section, and I'm not going to go through every slide because some of it's review of the last lesson, just written out a little more in detail. So you have a hard copy of these slides. It's just a kind of a different approach if you're still a little confused from the previous lesson. Describe basic properties of this term current, solve problems relating current, charge, and time. Distinguish between drift speed and the average speed of a charge. So what we're going to be talking about is when you flip that switch on your room there on your wall, how fast or how long does it take that charge to get up to that light bulb to turn on? Calculate something called resistance, current, and potential difference. And so again, that's really the basics of all circuitry. All the base equations are going to be based off of those three variables. And describe how and what factors affect resistance. All right, so we talked about the idea of a parallel plate capacitor, building up charge on opposite plates, creating this electric field, having a high potential to a low potential. We always talk about positive side being a high potential because, again, everything is in reference, thanks Ben Franklin, to a positive test charge, and they don't want to be so they don't want to be separated here. So it's like raising the rock is at a high potential, the ground level is at a low potential, and they're always going to flow from high to low. All right, so again, I'm going to skip through these. You have the hard copy of this. It's just talking about the parallel plate capacitor. All right, so let's talk about, we have the stored energy. We know electric potential, okay? We know this term measured in volts. We already hopefully understand that. And it's the potential for these charges to start flowing. Now, the flow of that charge is what we're talking about here, current, okay? Current is the rate at which charge flows past a point. I'm going to attach another video I I tend to show in class that does kind of a nice way of describing it. And a lot of times you talk about, or you hear voltage, current, resistance being talked about in terms of water flowing. And so that's kind of how we're going to do this as well, because it's a good analogy. Again, think of a river current. If I talk about a current in a river, you think about the river or the water flowing by you at a certain rate. Okay, if it has a high current, you probably don't want to go swimming. You're going to be pulled down or with the current. But current is the flow of charge. So when you see this term current, draw that in your head. What are you used to using? Most of you think about current of a river. Now we're just talking about the flow of charge. Okay, the flow of charge. That's what we're talking about with current. Okay? Current is the rate at which charge flows. Now, I'm all out of C's using variables. Okay, we got lowercase c, we got capital C, we have units for C. Capital I. Capital I is the symbol for current. Okay, capital I is the symbol for current. And at its base definition, the rate at which current flows, if you think about our old speed equation, the rate that distance is changing, it was distance divided by time. So current is literally going to be the amount of charge flow per time. Okay. Now, remember, a coulomb of charge is not one electron. It is a whole bunch, or a one proton. You know, remember, a electron or a proton is 1.6 times 10 to the negative 19th coulomb. So you can kind of think of it about this as buckets of charge, flowing by you per second. Okay? When you talk about, say, the flow rate on a faucet or your shower head, if you ever gone, it'll talk about, or a hose, or and something that's flowing with water, it's measured in gallons per minute. It's not measured in water molecules. So this is kind of the same type of thing if you think about it that way. So you have this bucket of charge, this gallon of water that, flowing by per in a certain amount of time. And again, it's just simply a ratio of charge, the amount of coulombs per second. Right? So good video, recommend you linking to and watching. But again, current at its base is coulombs, the amount of charge per time. Okay. So again, this is in coulombs, this is in seconds. So literally you're dealing with coulombs per second, but we have a special name for that, and that's amps. That's an amp. Okay, amperes. Now, an amp is 1 coulomb per second. It is a SI standard unit, so I can use any of my metric prefixes. All right. The particles. Now, here's where I told you you're going to get confused when we first started electricity, when we were still back together. The particles that carry charge through a wire in the circuit are your electrons. If you think of the structure of an atom, those protons are bound up inside, okay, of the atom in the nucleus. The electrons are the ones that are on the outside. Many of them, your valence electrons, you can transfer. You talk about doing ionic bonds and so forth. These valence electrons can be rearranged and moved and swapped around. They're a lot smaller mass. And so when we're talking about current, we're literally actually talking about electrons flowing, and thus the name electricity. Now, here's where it gets confused. Remember, we talk about the electric fields. Electric fields are drawn, everything we've done so far is based off of a positive test charge. So you have to understand that electrons are going to be going opposite. Okay? And that's actually what is flowing. Ben Franklin was, is the kind of the guru. You think about the old legend of him getting struck with electricity, flying the kite in a thunderstorm. He envisioned that positive charges were the carriers of charge, and that was thought to be true for a long time. So that is why the convention of current, directional wise, is based off of the proton, even though the charge is actually flowing in the opposite direction. Okay. So even though as we talk about the flow of electricity and we talk about the direction of current, we're going to draw it still as a positive test charge. But you have to understand that if you could see the charges moving, it's actually electrons, and they're actually going to be moving in the opposite direction. So the direction of electric current is by convention, is the way that we're going to do it, is the way a positive charge would move. So the charge is going to be moving opposite of a positive, out of a positive terminal, because where a positive is going to want to go, they're going to get away from their other positive. So they're going to leave the positive and return to the negative terminal of the battery. But understand, if you could actually see what was going on, it's the electrons that are moving the opposite way. So you have to be very, very careful with that. So if you connected a positive to a light bulb back to negative, they have to have a completed path, and we'll talk more about that. The direction of current would be leaving the positive, thinking of these positive test charges, and returning to where they want to be because they're attracted to the negatives. The resistance in here is too great. You're not going to see the positives jump through the battery. You're going to see them take the path that's easiest. It may be a little longer, but think about there being a roadblock in there. Now let's talk about the speed, how fast are they actually traveling. Now, with think of flipping on the light switch. Does your light take a while to get on or turn on, or is it almost instantaneous? So what I want you to kind of think about is how fast are those electrons? How long does it take that electron that's on the opposite side of your light switch, once you connect the path, how long is it going to take that single electron, if you could tag along with it, to get up to your light bulb in your ceiling? It's actually going to be longer than you think. Okay. There are tons and tons of electrons, atoms, all built into this conductor, your copper wire, and it's not going to take a direct path. There's going to be a lot of collisions, boom, 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 and it's going to be hard to get through. It's like a crowded, hallway. Now, with the current virus outbreak, the hallways aren't going to be real crowded, but imagine the whole high school being outside my room, or in my room, let's put it that way, and you have to get from one side to the other. It's going to take you a while to get there. Okay, and this actual speed is about 1 meter per hour. So in an hour after you flip the light switch, that electron that was right there by your light switch has only gone a meter. So how in the world does the light bulb turn on almost instantaneously? We'll go back to my analogy of my room. If my room was packed with the entire high school, surely a violation of the 6 foot rule. But as soon as you start pushing and moving, somebody's going to do what? Fall out that door, aren't they? And that's exactly the analogy I want you to think about. That wire in that room or in your wall is loaded with electrons. And as soon as the ones in the back of the room start pushing, that electron that's still sitting right by that light bulb is going to get pushed into the light bulb, is going to get pushed out of my hallway and be able to energize that light bulb. So that's why you see this difference between, what you think about the electricity coming on versus the actual electron and the drift speed of it. So let's look at a couple of pretty basic equations here. You got a CD player, if anybody even listens to them anymore, but think of like your MP3 player, your phone, you're streaming your music. Typically, electronics are in milliamps. And again, milli, you got to make sure everything's in amps. So we're going to have to change that. So my current here is going to be 5 times 10 to the negative third amps. Got to convert it. And how long would it take 2 coulombs of charge to pass through that area? So in other words, how long? Time. So the amount of charge is 2 coulombs, 2 buckets of charge, 2 gallons of water. Remember, that's not just single charges. And so current is the amount of charge and the time. So you got your 5 times 10 to the minus third amps, the amount of charge and time, and plug and chug, it'll take about 400 seconds. All right, I'm going to do one more. I have some other ones loaded there you can practice, but they're all kind of based off the same. In a particular TV tube, so Coach Miller's old television tube, the beam current is 60 microamps. How long does it take for that many electrons to strike that screen, to illuminate the screen and give you the picture? Okay, now that's electrons, that's not charge. So if you want to know what the overall charge is, you're going to have to take that 1.6 times 10 to the minus 19th and multiply it the amount of charge, the amount of electrons that you actually have. So the actual amount of charge you would have over time is your current. Okay? And your current, it would be 6 times 10 to, okay, the minus sixth. And you should get about 1 second. So again, there was your current, it would just be 60 times 10 to the minus sixth. The only trick here was understanding that they give you the amount of electrons and you need the actual amount of charge. So that's why we multiplied the 3.75 times 10 to the 14th, because each one of them had that amount of charge. All right. Let's talk about the third part of it, resistance. Okay. Think of resistance as friction. Resistance in a circuit is the amount, it is the resistance that the charges have to flow. Think about it again as friction and things that are going to cause these electrons to have a harder or more difficult or an easier time to flow. High resistance, they're going to have difficulty flowing. Low resistance, they're going to flow real easy. And there are going to be a variety of factors that are going to affect this. Okay, so right now we have potential difference, voltage. Okay. We have current, that's the flow of charge. And now I have R, resistance. Think of voltage that's related to that's your stored energy. If you think about it in my analogy of water, this is like having a pump pressure, okay? Or a water tower height. The higher that water tower is, why do you have water at a very high? Because you have a lot of potential energy because of the height. Greater voltage, you have a taller, a stronger pump, or you have a higher water tower. So you're going to have more pressure ready to flow. So think about it as pressure. Current would be like your flow rate of your gallons per minute. That's how fast that water's flowing through. Resistance are going to be those things that are going to restrict the flow. How long are the pipes or the hose? What's the diameter of the hose? Is it a big fire hose or is it a tiny little garden hose? What might it be? Okay. So one thing that might affect resistance is the length. How long is it going to flow? So in a garden hose, the longer that hose is, the slower that flow is going to be because it's going to have to travel a lot longer till it gets to you. So that's one way that's going to cause the resistance. Basically, you want to think about it is what is going to slow it down? What is going to cause more and more collisions between those charges before it can get to where it needs to go? The end of the line, the light bulb, or in our analogy, the hose. The other is going to be the diameter, okay, the cross sectional area. If you have a big, wide open wire, it's a big, large diameter, it's going to have more area to move without collisions. Just like a fire hose versus a garden hose, same principle there. The third is the amount of material. Certain materials are better conductors. They have a lower resistance. They allow charge to flow easier versus things that are closer to an insulator. So, kind of the three variables that are going to affect your resistance is the length that it's going to flow, the diameter of the wire or the conduit that or the material it's going to flow through, and also the material. Okay, resistivity. This is just a measurement of how easy it's going to flow. Now, I haven't talked about it yet, but ohms, capital OHM, is the unit for resistance. Okay, and you see that wonderful symbol, omega. Okay? So this is the symbol for the units for ohms for resistance. And we're not going to use this, but just so you know, if you want to find the resistance of the length of, say, a wire, typically is what this is used for. You have that resistivity constant, which you would look up for that material. It's like the density, the length, and the cross sectional area of that material. So if you're going to wire a house or you're running electric lines long distances and you have to run a certain gauge wire, certain size of wire, this is where it's coming from. Ohm's law, V equals IR. Okay. This is the equation that you are always going to come back to with electricity, Ohm's law. Okay. This is your potential difference. This is your current. This is your resistance. This is measured in volts. Oh, sorry. This is measured in amps. And this is measured in ohms. Again, the symbol you see is that omega. That is the relationship anytime you're dealing with wiring, circuits, whatever it might be, that it's always going to come back to. All right. So a 1.5 volt battery is connected to a small light bulb with a resistance of 3.5 ohms. What is the current flowing through that bulb? Okay, potential difference voltage is 1.5 volts. Your resistance is 3.5 ohms. Okay, and I'm trying to find current, VI and R, Ohm's law. So 1.5 current times the resistance of 3.5, and you'd be dealing with 0.43 amps or 0.43 coulombs per second. Stereo with a resistance of 65 ohms is connected across a potential difference of 120 volts. What is the current in this device? So the voltage is 120 volts. The resistance is 65 ohms. Again, trying to find current. So V equals IR, 120 current times your 65. The flow rate would be 1.85 amps. Find the current in the following devices when they are connected across potential difference of 120 volts. Work that one out. If you have questions on it, You got a hot plate and a microwave. Okay, hot plates has a high resistance. That's why it's producing so much heat. And we'll talk about that, I believe, next section. But you get about 2.5 amps here, and you get 6 amps here. Current in a microwave oven is 6.25 amps. If the resistance of the oven circuitry is 17.6 ohms, what is the potential across? All right, so V, I, and R. So you got 6.25 amps, you got 17.6 ohms, and you will need to be connected to a 110 volt source, a typical household outlet. All right, draws 2.5 amps. So there's your current, potential difference of 115. And what is the resistance? So 115, there's your 2.5 times your R. And so the resistance would be 46 ohms. And the current, a certain resistor, when it's connected to a potential difference, what is the current in this same resistor if the operating potential difference is 90 volts, 130 volts? All right, now keep this in mind. The resistance is a function of that component, so that's not going to change. So once you know what the resistance of a system is, that stays constant. What's going to change is and tweak is your voltage and currents, like kinking the hose or not kinking the hose. Okay? So for you have to figure out what the resistance is first. Okay. So what is the resistance of this system? So you're given initially a voltage of 110 and a flow rate of 0.5. So using, again, everything's going to be based off of Ohm's law, 110.5 times the resistance. Your resistance would be 220 ohms. That's going to be the resistance for that system for everything you do in this problem, unless you change the components. So for A, trying to find the current, I now plug it into a 90 volt source. So 90 would be the current times that 220. The flow rate is now going to be 0.4 amps. Okay. Now you notice pressure, height of the water tower. If you have less pressure behind it, okay, you're going to have a slower flow rate, and that's what we figured out. So for B, I have a higher pressure, a higher water tower, a bigger pump trying to pump that water in. I should see a larger flow rate. So V3 is 130 volts, which is I times still that 220, and that flow rate would be 0.59, a higher flow rate. As always, if you have questions, please make sure you email me, get a hold of me, and we'll get them figured out.